Okay, so I'm very happy to introduce our next speaker, John Brota, and he will talk about deconstructing dynamics in QBism. Here we go.
All right. Thank you to the Philipps for organizing and giving me the opportunity to speak. Am I live? Am I working? Yeah. Okay. I'm really delighted to be here. My plan is to share with you a ongoing and I have to click it again. Okay, now it should work. Ongoing work with my QBist co-conspirators, Chris Fuchs and Rüdiger Schock. And I'm very happy also that Rüdiger and actually several other people have set the scene by mentioning QBism, because that means that I don't have to defend QBism in my talk. I can just tell you about some new developments that we are working on in it. As you can tell from my title, I'm going to talk about dynamics. So very briefly, the outline is going to be, first I'll tell you what the problem is that I'm actually going to address. Then I will showcase one aspect of the way that we are starting to rethink the way we think about QBism that resulted from thinking about it, and then solve the problem, and then open the floor up for your questions. So first, although it's been introduced, let me just give you a very whirlwind review of what QBism is. So as Rüdiger said, it's a doxastic interpretation. It's also a reconstruction effort and also a ontological project. On the ontological side, what we're doing is we're seeking physical principles which compel quantum theory. And in doing so, as Rüdiger emphasized, we are guided by the interpretation. And what is the interpretation? Well, in a slightly longer phrase than Rüdiger used, basically, QBism says that the formalism of quantum theory is an empirical addition to Bayesian decision theory. And so the consequence of that is that the objects of the theory are personal. So that means things like the states, the channels, and the measurement operators. But it's sort of another way to answer the question from in the back row of the last talk. The structure of the theory we would think of as interpersonal or objective. So an example of that is, for instance, the Born rule. And really what I mean is the entire inferential reasoning structure itself. Of course, the subject-object distinction is really more of a spectrum. But the point from the ontological point of view is that we wouldn't want to look for reality on the most personal side. So I can illustrate that with a little friend here that I drew with his physical system, which is, of course, canonically a cube, which he's pondering actions on. And the sort of normal attitude to take is that the quantum state is a property of that physical system. But QBists say no, because the quantum state is an object that you use for your decision making. It actually lives inside your head, or if you're, an entire research team, it's part of the reasoning structure. It's not part of the world. Okay. So if it doesn't live in the object, then where should we look for reality? And for that, the basic gist of the goal, as Rüdiger told us in the previous talk, is to try to sort of reverse engineer the decision framework and guess what kind of reality might be making it the right one. So within the decision framework, measurement, not the measurement operators, but measurement itself is the thing that's making closest contact with the physical. So to borrow a phrase from Chris Fuchs from the paper that coined the term QBism in 2009, we are such stuff that measurement is made on, which is itself a riff on a Shakespeare quote. So basically what we want to do is look right at the interface between the subject and the object, the agent and the system, at the action or event itself, which gives the agent an experience and the world novelty, presumably, at about the same time. This is part of the idea of reality as a verb, not a noun. Nouns are just really slow verbs, is basically the idea. So let's do that. Let's zoom in on the interface between this agent and his object. Oh, there's the picture. There's the talk. And woof, okay, now they each have hands. That's great. And so now basically when you take an action, there's a spark. And the heuristic idea of the direction that we're looking for from an ontological perspective is to try to find the reality in that spark. All right. We can contrast this with what I'm calling the clock. So the clock is the sort of traditionalist physics approach where the real thing out there, the thing that is actually part of the world, is the dynamics and the state, and you just evolve. And basically, I've illustrated the clock with God's immaculate wristwatch here, which just turns, unthinkingly according to the Hamiltonian of the universe, and then we're done. But see, you're not done, because from such a viewpoint, what you have to do is then come up with some way to explain away why the quantum formalism looks like it's a decision theory. You have to be able to eliminate agency and measurements and view them as derivative of dynamics, which just happens. Such a view, of course, is going to be comforting from the classical physics perspective, but we're not here to be comforted. We're here to try to understand. And we think that such views are ultimately going to be untenable because they are ignoring the fact that we're dealing with a fundamentally different kind of theory. Okay, that brings me to the problem, dynamicus problematicus. QBism, of course, demands exactly the opposite. Rather than viewing agency and measurement as derivative of dynamics, we want to view dynamics as derivative of measurement and belief in general. And so far, one can do that at a first order level from a very, very naive objection to the idea. We can answer it very quickly. So basically, someone might say, hold on, dynamics can't be part of my belief because dynamics tells me how something changes. And really, then if I think about how states just evolve, then why would I call that a belief? If something mindlessly tells me how it changes, why would I call what it tells me how my beliefs change? Then why would I call that thing a belief? And the answer to that is very easy. From a decision theoretic framework like QBism, you basically just say, oh, that's fine. Dynamics is not about how real states do change in time, but rather about how we expect our beliefs to change in time when we're not taking actions. So, of course, our beliefs change in time when we take actions, and perhaps they change in time when we don't take actions. Dynamics is about the latter. But, of course, this is kind of a trivial answer, and it begs the question that Harvey Brown put very nicely when he said, well, okay, but why do you expect your beliefs to change at all, unitarily or otherwise, if you do nothing? And to make matters worse, there is a story, or maybe I could call it a fable, in not just foundations, but in the wider physics community as well, that is non-cubist, but nonetheless, I would say quasi-epistemic, that from which many derive extreme explanatory power, that tries to view dynamics in a particular way. So this first part, basically, this is an understanding of dynamics and in particular decoherence. So the story goes like this. You have two systems. One you call the system, which is the cube, and then another system, which we'll call the environment. And you imagine that they're initially decoupled, and then there's some interaction Hamiltonian between them. Some joint evolution followed by tracing out the environment gives you a completely positive trace-preserving map on the system, otherwise called a quantum channel. This is just math. That's part of working with a larger Hilbert space. No problems there. But the story starts here. So physically, they ask, what's going on? And the story that you often hear, and we heard it before in Lucy's talk, and I heard it from my quantum optics professor. Basically, what you imagine is that the environment or something in the environment is monitoring its part of the system and recording outcomes in the wind in this scroll, writing and it's measuring in some basis and it's getting some outcomes that we don't have access to directly. So basically, since we don't know the outcome or the basis of that measurement, that is because we do not have access to the so-called measurement record in the environment, there are two consequences. First, we form the CPTP map that we talked about before simply by averaging over the post-measurement states in some basis. So we had to do the trace. We choose a basis now, and that's equal to doing the trace. And then the ignorance that we have of the basis of that particular measurement accounts for the fact that the isometrically invariant, so basically unitarily remix invariant sets of Krauss operators, which are the name of generalized measurement operators, they all will define the same channel. So, okay, that seems like it's explaining two things very nicely. So carries enormous explanatory power. And it is also dressed in some epistemic notions. So like, for instance, we're talking about what we know and don't know, and we have the ignorance about this. But from a QBist perspective, this is unsatisfactory because, well, it inclines people to slide away from QBism and more towards an ontic understanding of states and evolution, as we also saw with the difficulties of trying to bring decoherence into RQM. So, okay, here's our agent thinking about the measurement record, and then he starts to get unsatisfied. So, here's a couple of complaints. It's actually irrelevant to us, of course, thanks to the math we saw before, if someone measures their system. Our local state is going to be unaffected. So what have we really gained by imagining Eve, the environmentalist, has measured and stored an outcome? And another, perhaps more serious issue is, if these supposed measurement records were in principle accessible, then it sounds like hidden variables. I'm kind of constructing some straw men here. I'm going to apologize for that on the next slide. Don't worry. But the point is, it seems to imply a third-person view is possible. And from some general epistemic types of considerations that don't just commit you to QBism, we should be a little bit suspicious. But most importantly for me here, since I'm not defending QBism, I'm just simply working within QBism, it's not clear exactly how to articulate the story. The most importantly reason for that is because if the environment is measuring, then it has to be another user of quantum theory. And for me, a user of quantum theory is a decision maker. And it seems a little silly to regard the local electromagnetic field around my cavity as a user of quantum theory. So instead of viewing this, these problems as problems, let's view them as opportunities. I told you I didn't want to knock down any straw men. So instead, the goal of the talk is to explain how I believe we have risen to the challenge to try to articulate a consistent and more complete QBist account of dynamics. And as I also advertised at the beginning, pursuing this has spurred an exciting perspective shift in QBism more broadly. So let me tell you, let me sketch what that perspective shift is, and then we'll go through it in detail. We're calling this the strands of normativity, but that name may not stick. We'll see. But here's the gist. Usually, we have thought of quantum theory as a single normative unit or monolith that just sits on top of standard decision theory. So here's a schematic of that. We have decision theory, which is obviously a square. And or quantum theory, or QBism for me, is a rounded square that just sits on top. But now we're thinking more in terms of an increasingly structured normative additions kind of structure that's indexed by the judgments and beliefs of an agent. And I'm very happy also how much detail Rudiger went into about the word normative, so I don't have to tell you so much about what I mean by that. But here I've illustrated a fantastically complicated looking monster. Or rather, it's something that looks quite a bit like an onion. And that is the new structure that we're going to go through layer by layer. So the idea is that each layer, which I will explain in detail coming up, is characterized by a new belief or judgment that your agent can adhere to, and when they do so consistently, it adds structure and constraints to their reasoning. And of course, I couldn't resist, since this looks like an onion. We're talking about quantum theory, so there's layers. I had to make the Shrek meme. Quantum theory has layers, as he explains to Donkey. I don't know if this is going to land well with people, but anyway, maybe it's the wrong audience.
I'm too young for that.
You're too young for Shrek? No one's too young for Shrek. All right. Okay. So let's. So another thing we realized when articulating this, I mean, maybe this isn't a new realization, and some of the grounding in the phenomenology this morning has made me wonder whether some of this early stuff has to be massaged a little bit. But basically, the point is, these first three layers I'm going to call pre-quantum experience, because we don't actually encounter quantum mechanics yet. And we're at a quantum conference, so I'll try to go through them relatively quickly. The first one, using a term borrowed from phenomenology, is the life world. I'm actually not positive that I'm using this term in exactly the right way. I got some hint that maybe these first two layers need to be combined, but it's not going to be a problem conceptually. But basically, we're assuming that there is an entity called an agent, actor, or user that can act and experience. And at this stage, basically, I'm not going to assume that the agent conceptually differentiates between different experiences or even different actions. They're just living their life. And also importantly, at this stage, they are not adopting consciously any normative constraints. So a normative constraint is, Rudiger gave the example of quantum theory as one really big normative constraint. We're breaking everything into little parts, but normative constraints like the Born rule or anything more pedestrian are not being assumed. I have a comment, of course. Just so you know and don't think that QBists think this, we're not claiming that agency is like primordial, just that it arises at some point. And I'm not going to speculate here about how it might arise from whatever is ontologically prior at the moment. Okay, next level is when we are going to differentiate the experiences. So the agent makes distinctions between atomic experiences and possible actions, but they still do not consciously adopt any normative constraints. I should also point out that these distinctions are judgments, just like everything else is in the structure. They're not objective. It's more like differentiating colors is up to, the agent or the eye of the beholder. Okay. And now, finally, we reach decision theory, which was the starting point of the little two-block structure that I showed earlier. And in particular, I mean Bayesian decision theory. And for that, of course, I refer to you to the Bible by Bernardo and Smith. Basically, decision theory is about preference. So if we want to have some sort of guidance for making decisions, I need to have some notion that I prefer one thing to another. And the way that you get at the standard notion of Bayesian decision theory is you assume a particular kind of mostly unobjectionable preference structure. And then from that structure, you can derive that the particular kind of guidance that decision theory gives you. So, for instance, the one kind of structure that you assume is that your preferences are transitive. This is not necessary in general for people to have such preferences. But if I prefer A to B and B to C, then it's reasonable in a lot of circumstances that I would prefer A to C. And basically, you take those preferences together and you argue that the agent should never prefer a sure loss. So when you're taking an action, I should basically try to take the action that maximally benefits me. Or sorry, not the action that maximally benefits me. I should try to be in expectation most satisfied with my decision. And in the process of proving that, the structure of probabilities, along with utilities, co-rise into existence normatively. And you find that the rational choice, so-called, is to take actions that maximize your expected utility. So, okay, we don't actually need utilities right now, but we do need probability theory, and that's part of decision theory. So now at this level, we've assumed that we have an agent if they are adopting if they have the appropriate kinds of preferences and normatively subscribe to the idea that they should take actions that avoid sure loss, then they end up someone who can use probability theory perfectly, but we're not ascribing them any further structure. One last comment, one first comment really on probability theory is that this is a norm, not a description. So the rationality idea is, of course, an idealization, which is something that one might or perhaps should strive for, but possibly never reach. And from a psychological experimental psychology perspective, humans are extremely poor at being rational agents. So I'm not talking necessarily about humans as they are, but maybe humans as they could be or might have been if we were better. All right, so here's a good time to emphasize something that I often sort of see treated suspiciously, which is that probability theory is not classical in a classical mechanics type of sense. And the reason for that is because, as I just told you, the structure of decision theory comes directly from agents' preferences. So naturally, the natural world where the agent lives is going to be indirectly influencing it. But from, at a first level, decision theory and thus probability theory are agnostic to the physics. So if you do want to have a decision structure that obtains some guidance from the physical world, or your experiences with it at least, then you have to distill that from your empirical experience with the external world. So one very successful addition, which I will put in a dotted line around here, is to make the classical physics postulate that systems are completely characterized by this coordinate system of position and momentum, Q and P, in a so-called phase space. And you also, of course, adopt the Hamilton's equations, a set of coupled differential equations that tell you how phase space points evolve. So it tells you exactly how the dynamics works in your system, the dynamics that just happens. So don't forget, we have our clock here. And it just goes along like this. If you want to then use your probability theory, you would have a probability distribution over phase space points. If you say don't know exactly which phase space point it is, that's called a Liouville distribution. And if you wanted to say estimate the expectation value of some observable, you just compute the expectation value of an indicator function and go to the bank. And this worked really well until it didn't. And it stopped working really well in about 1925, and then broke even more deeply when Cauchy, Becker, and Bell basically proved to us that the idea of a coordinate system of ontic states is just not powerful enough to capture the diversity of experience that modern science can elicit. And importantly, the idea breaks right at the beginning, before any notion of dynamics. So that means we can sensibly doubt that dynamics just happens. All right, so now we finally reach something that's quantum. And here, I'm not going to go in depth because this is really just a passing stage in what we're trying to get to for the purposes of this talk. But what I just want to say is, and we all know this, of course, but essentially the addition that works to the decision theory from the decision theory perspective is to invoke structure isomorphic to a density matrix for your state, a POVM for your measurement, and to say that those two are related to your probability assertions via the Born rule, which is this. And Rudiger was very careful to point out how this is a normative structure. So in fact, this is this basically all of this really is the judgment that the agent assigns at this layer. I just want to repeat a new way of talking about how to interpret this normatively that Chris actually invented 2 days ago that I really like and I think is very instructive. So essentially, what people, as Rudiger said, what people would typically want to view this as something that takes as input rho and EI and has one output, which is the probability. But a better way to think about it is that the Born rule is a relation in QBism that takes three inputs, which is this, and that, and has one output. And that output is consistent or inconsistent. And inconsistent is if it doesn't equal. So you're setting all three, by just considering your beliefs. And then if you notice that they don't hold up, then you've detected an inconsistency in your reasoning and you have to go back to the drawing board. But just like probability theory, quantum theory, or at least this layer of quantum theory does not tell you how to fix that judgment. And of course, the character of the world which entails this particular kind of addition is more subtle. That's why we're all here. But for the purposes of this talk, I'm going to assume it because we're going to be using it to talk about dynamics later. So a comment. Earlier, I had the life world, I didn't have anything. And then I had I, because we had differentiated experiences and we were labeling them by I, okay? So, and then we had P of I, so because we had probabilities. Well, now we have E of I. So now the experience is actually represented by E of I instead of just I alone. So each layer that we build up onto this onion is adding and enriching the concepts that appeared earlier. Two more comments. We are far from full quantum theory. I mean, there's no dynamics, first of all, but there isn't even post-measurement states at this stage. We're literally just talking about the decision right in front of us and the outcome that we might get. And I think another important thing to point out at this point is that we're not deriving, like, for instance, any of these structures from unitarity on a larger Hilbert space or anything like that. These just are the primitive concepts as someone would talk about them in, say, quantum information theory, like in Nielsen and Schwang. That's their starting point, and that's good enough for us as well. All right. This next layer actually does begin to allow us to relate different moments. So previously it was just, I have one decision in front of me and I'm going to take an action and I'll get an outcome. But now we might have beliefs about what our own future beliefs might be. The reason we call this reflection is because of, that's the name given to it by von Frossen. So this is von Frossen's reflection principle. And this is something that you can formulate without quantum theory. It's just an extension of the preference structure that I was talking about that gave us decision theory in the first place. But now it's about avoiding sure loss according to your beliefs that you have across time, or at least across moment-to-moment action. So I'll explain to you the consequence of it in a second, but first point to make is that it carries over directly from to quantum theory without issue. Chris and Rudiger actually wrote about this about 10 years ago. So here, let me illustrate what I mean by reflection. So basically, a little guy says to himself, if I plan to measure EI, and then if I get outcome I expect that I will then, for further gambles that I might make in the future, use the state rho I. So for each one of these EIs, I assign, or I have an expected rho I post-measurement state. So if I plan to make that measurement, then right now, if I have to gamble right now on subsequent measurements, the state I should use is the convex mixture, or the expected value of those post-measurement states, where this P of E is the Born rule probabilities for this measurement. Okay, so that follows from the extension of preference structure to avoiding sure loss across, to beliefs across time. And another point to make right here is that these post-measurement states are not constrained. It's completely open. Literally any state could be something that the agent might expect to assign if they get some particular outcome. As long as it's another valid state, they've already committed themselves to having to use quantum states, i.e. trace one positive semi-definite operators for systems. But regardless of how they get, or regardless of which one they choose, it could be one that they say that they will assign if they get outcome I. So as a sort of functional, it could be a function of rho, the entire state. So it could be contextual, it could be nonlinear, anything goes, as long as you actually get a valid state out. All right, so now it's my turn to make a riff on a Shakespeare quote. So here's poor Juliet. She's looking wistfully into the future. She knows how she would gamble now. She knows how she would gamble, or she knows how she should gamble now about. Sorry, I'm trying to make this analogy work. She knows how she would gamble now about outcomes of future measurements if she had to gamble now and she was going to learn something in the middle. She has her reflected state in everything. But her parents have said that there should be no relation between expected post-measurement states and reflected states. And she thinks that's unfair. She says, what's in a name? That which we call a reflected quantum state by any other origin would function the same. So what the hell am I talking about, to quote Adon Cabello? Basically, this level is specified by the judgment that a reflected state is on equal footing with any other. So if you decide to feel that way, this argument is due to Blake Stacey, by the way, then there's consequences for your post-measurement functional. And first of all, that judgment implies that the post-measurement functional is insensitive to the difference. So we can illustrate this with consecutive measurements, that two consecutive planned measurements. So say you are planning to measure lambda, this POVM, and then later the POVM EJ. Okay, so phi is my post-measurement functional. So phi rho I is phi, which takes as input my current quantum state rho, and then say this, I got the particular outcome lambda I. Okay, so I got this post-measurement state, or I imagine I could get this post-measurement state. I expect I will if I get this outcome in the future. And then in the next measurement that I could make, if I get the outcome EJ, then I use the same functional again, of course. And I have these two inputs. So this is the one from this output, and then this is the effect EJ. And so if I try to reflect on that whole procedure, then I should use now the reflected state for gambles that would take place after obtaining outcome EJ with the probabilities for the lambda measurement, mixing together the post-measurement states for getting the EJ outcome. All right. But there's another way of thinking about the same the same process. Ultimately, we could say, what if I reflected first? So I'm going to take this lambda measurement first, and okay, when I'm contemplating the EJ measurement in the middle there, I will use the reflected state of the post-measurement state, this post-measurement state here. So this is the reflected state that I use when I contemplate my EJ measurement. So then why not just use that right here in the functional? This judgment says that I should, because it's just another state. So in that case, the state I should use for gambles now about actions that would take place after obtaining the outcome EJ is here. And you can see the difference between these two is that I'm able to pull the sum inside the functional, which implies that the functional is an affine map. All right, and that's why we call this whole layer affinity. So, okay, that judgment gets us down to affine maps, but affine maps are not the same as the maps that you have in quantum theory. But I want to emphasize something right now, which is that we're free to stop at any layer along this in this onion, in the sense that we end up with a valid theory that the agent actually has to subscribe to normatively, even though it's different from textbook quantum theory. And actually, this one has precedent. So not completely positive, and in fact, even not positive maps can appear in some circumstances. Most notably in the work of Anil Shaji over the last 20 years, and he started that with Sudarshan. In these cases, it's appearing in the context of unitary evolution on larger Hilbert spaces, where in general it happens when you think about your system and environment as initially correlated. But for us, it appears before invoking either. So this is a feature, not a bug. That said, we do want to get to complete positivity, so let's get there. So here we are on the outside in a layer, which is actually really two layers, but for brevity, I'm condensing it into one, which we call extendability. So the first layer is we just get to positivity, and that's very simple. If I assume that the phi that you end up with could take any valid state as an input, then and also always give a valid output, then it actually has to be a positive map, not just an affine map. So the second, this is the part where the extendability comes in. We think to ourselves, well, okay, if my system of interest were considered a subsystem of a larger Hilbert space, so a subsystem of some bigger system. So for instance, if my cube were actually a cube that's also in a larger Hilbert space with this octopus, then the larger Hilbert space is the Hilbert space of the system and the Hilbert space of the octopus. And if the agent judges that the post-measurement functional, which they know to be positive thanks to this part, that corresponds to an action merely on the system of interest, namely the cube, they don't want to act on the octopus. If they judge that it should have this form, that it's equal to the phi from before, but then tensor the identity, well, then that is just the definition of complete positivity.
Why on earth of octopus?
Why not? It was fun to draw it. Anyway, it doesn't have to be an octopus. It could be an electromagnetic field or something more boring. But anyway, once we have complete positivity, we've actually essentially gotten to textbook quantum mechanics, at least minus dynamics, because the complete positivity implies a cross operator decomposition from which one can find a set of cross operators with the sole restriction on them that A dagger A is equal to the effect from the POVM. So that's a POVM element. And a consequence of that is that our post-measurement functional has to actually take this form. So this form is familiar, I'm sure, to many of you as the typical post-measurement state that's prescribed in quantum information textbooks. So we've arrived at the normal full quantum theory experience as far as measurement is concerned. And I should also point out here that the experience is enriched once again So now effects have been replaced with Krauss operators, and the actual experience itself now encompasses the expected post-measurement commitment as well, because we know that we update like this, or we expect to update like that. Some final comments. Nothing formulated depends on the dynamics. So again, we're not talking about Krauss operators that we got by tracing over an environment or anything like that. And I should also say that the Krauss operators come from the possibility, not the actuality of acting on a portion of a larger Hilbert space. Okay, so that was our whole onion. And I'm going to call the onion essentially quantum action. What do we have? We have a fantastically powerful decision structure, which grew layer by normative layer. And I also emphasized that depending on one's beliefs, resources, concerns, etc., stopping at any layer is valid. So, I mean, a common place to stop would be right here if you're only considering the next measurement, or maybe your action will destroy the system, for instance. And then one final thing, the whole structure is normative, which means that objects appearing later may aid in eliciting those at other or lower layers. So maybe I have reasons for having a strong commitment for Krauss operators that might help me set my quantum state, for instance, even though that appeared lower in the hierarchy. Okay, so finally, we have quantum action out of the way. This whole blossomed out of us thinking about dynamics. So let's talk about dynamics, or what I like to call quantum inaction, because action was about how you expect your beliefs to change when you do take an action, and dynamics is about how you expect your beliefs to change when you do not. Okay, so let's imagine 3 discrete moments in time. So I'm just talking about discrete time. So these are consecutive moments. T0 is now, T1 is the next moment, T2 is the moment after that. Let's say rho is the state that I assign for actions on the system now, so T0. And then rho of T2 is, which I will stylize with a functional acting on the original rho, is the state that you expect to assign for actions at T2, given not acting at T1. So of course, this is the one you expect. So I actually have this commitment also right now. Everything is happening right now. I'm never going to leave now, formally speaking. But that's my expected state that I'll assign at T2, given not acting at T1. So again, similar to reflection, if I must gamble now on an action that I will take at T2, given that I'm not planning to act at T1, then of course I should use this state. Okay, no problem. But this is, of course, the trivial story that I told before. I just gave you a few more latex quantities, but nothing's really changed. Now we're going to flesh out dynamics by characterizing it as the resolution of a normative struggle, which is a very QBist thing to do. Anyone who has seen a talk by Chris Fuchs has seen essentially this diagram. This is not actually directly relevant to what I just said, but I'm using it as a motivator because we're using the same kind of mindset. This diagram is an illustration essentially of the Born rule, where from a QBist point of view, I told you that it was an object with 3 inputs and 1 output, consistent or not consistent. The QBist rewriting of that can be done in terms of probabilities for 3 separate experiments that you could do. One important thing to say about this is that it's atemporal. So this is not like I'm going to make one measurement and then the next measurement. We're contemplating at the same time 3 separate experiments that you could do. So one experiment is I take my cube and I measure DJ. This is some POVM. It's arbitrary. Another experiment I could do is I take my rho, a different hypothetical or sometimes counterfactual measurement I could do is measure this POVM up in the sky, which we take to be a reference measurement. And formally, it will have to be informationally complete. And then the third experiment that we do is given one of these particular sigma i's that correspond to different outcomes of this, if you were to make it, then we make the DJ measurement. So for each of those, we have probability assignments. We have a conditional for this path, and non-conditionals for these 2. We view this whole path up here as a hypothetical measurement. And this is sort of what you're actually planning to do. And the point is that the Born rule furnishes a normative relation between the hypothetical and actual paths. Okay, so that's how we understand the Born rule. And actually, we can understand the current situation in a very similar way, except now I am going to make it temporal. So now I have my T0, T1, T2 as before, and we're going to consider a hypothetical measurement that we make at T1. Of course, we're not actually ever going to leave T0, but we're considering our expectations in time. So hypothetically, I could make a measurement at T1. And if I do that, then of course, I expect to have this post-measurement state. These are now Krauss operators, I should emphasize. And okay, so we can compare planning to make the measurement up here and planning not to make the measurement. So if I have to gamble now, if I'm planning to make the measurement, I have to use the reflection principle, as I told you before. So if I'm planning to measure, then I should use this as the reflected state because this is the probability. So when I mix with the probability, we just get the numerator here and we sum over I. And if we don't plan to measure, then you should just use the state that I talked about earlier, which was our beliefs about our present initial beliefs about what we should do if we don't plan to measure. And so now basically it all falls into place. You can see where dynamics comes from, and it comes from the judgment that a hypothetical measurement at T1 is irrelevant for my decisions at T0 regarding actions at T2. So if I happen to judge that, then that's what dynamics is, because that's going to lead to equality between the two paths. Said another way, planning to make a particular measurement doesn't change how I would gamble now about subsequent actions. So as I said, if we actually are contemplating a measurement that we consider to be irrelevant in this way, then we have to have that the bottom path version of what we would use to gamble and the top path version of what we would use to gamble are equal. And this is a very familiar expression of a quantum channel. So another thing to mention is, of course, just like everything else, the relation is normatively fixed. This is also a functional that has, or this is also a relation that takes three inputs and has one output. The output, of course, again, being consistent or inconsistent. But now we can tweak the state, the measurement, the Krauss operators, or the channel itself. So we try to find a way in which all three of those actually comport with our beliefs. And so I should also point out that, of course, I wrote this down in terms of Krauss operators, but I told you we could stop anywhere in the onion. And so if we get only to the level of reflection, then the most general kind of channel is going to just be this, where this is literally any map that gives you a quantum state given a quantum state. So that pretty much doesn't rule out anything, but you could stop at interesting places along the way, like an affine map or a positive but not completely positive map, for instance. And this could be another valid kind of quantum dynamics. All right, comments on dynamics. I would say that, or we would say that this unpacks why we might expect our beliefs to change when we do nothing, because it relates exactly to how we expect our beliefs to change when we do something. This ties dynamics directly to measurement and to the perspective that the only way to change the world is to act on it, which is very key to our interpretation. One technical term is that there is no non-selective measurement here. Non-selective measurement is sort of the idea, which is a non-QBist idea, that you can make a measurement and then forget or somehow not actually obtain an outcome. And then people end up with a convex mixture over the outcomes. But this is a strained or nonsense to a QBist, because for us the outcome is itself the experience. So what the heck does it mean that I had the experience but I didn't? It doesn't make sense, and we don't know what measurement means unless you actually have the experience. Another important thing to point out is that consistent treatment of all of this did not require us to think beyond the binary of the agent and the system. So I didn't have to mention environments anywhere. I didn't have to draw that eye writing on a scroll anywhere. There was no environment, there was no octopus, and there was no record. All right. So now let's just look at some two quick examples of very important notions of dynamics and see what we have to say about them. One kind, of course, is unitarity. And since what I described before was completely general, there is evidently no conceptual difference between unitary and non-unitary dynamics. The only thing that's going on here that's maybe different from the general situation is that the hypothetical action that we regard as irrelevant right now for our beliefs about future actions is the identity POBM. And the identity POVM is going to have a single Krauss operator, or at least it can be chosen to, where that Krauss operator is just a unitary. So some particular unitary is how we characterize the measurement of the identity POVM. But of course, there is still a measurement underlying it. Another equivalent way to say this is that you think that all non-trivial hypothetical measurements would make a difference. That's sort of what characterizes unitarity. And I caution you to say that with the point that although trivial, one thing that is very clear from all of this is that an identity POVM measurement is not the same as doing nothing. Doing nothing is formally doing nothing in a decision theoretic sense. An identity POVM is taking an action which happens to be at the boundary of the kinds of actions that quantum theory dictates are possible. And I would also say that this sheds new operational light on what I believe, at least for a qubist, should be old language of a so-called open versus closed system. Because instead of closed, we're now going to say things like, oh yeah, the hypothetical action irrelevant to our present beliefs is the identity measurement, or an identity measurement. All right. The other situation that I want to talk about is continuous measurement, which can also be brought into the unitary situation if we want. But everything generalizes straightforwardly to the continuous setting, where continuous measurement now underlies continuous dynamics. And continuous dynamics is really where, a lot of the applied physicists want to go. So we have to have a coherent understanding of this. So in a Markov approximation, let's just say we make one, where what that means is that my measurement operators do not depend on the entire history of my measurement record or the time of then I have some device that can give me clicks. And if I get a click in some differential dt, then my post-measurement state comes from one kind of Krauss operator. Which, is M mu or something. And don't worry about that for now. And if I don't get a click, then I apply a different Krauss operator. So the fact that I've actually factorized these in this particular way just comes from the details of it's a way you can write it down in thanks to the Markov approximation and Krauss operators. But formally, we're just talking about a particular measurement. And we should be able to derive what people would call the Lindblad jump operators. And this is a Hamiltonian from our commitments about the measurement. And so therefore, together, these two ways of measuring or of applying a Krauss operator with my post-measurement states that I would expect will give me a quantum trajectory that is conditional on my measurement record, a click or not click for each individual discrete time or continuous differential time that I've talked about. And so we could say at T0, my reflected state for measurements at some later T1 is then going to be the average over trajectories. And that's going to amount to solving the Lindblad master equation, which is the thing that appears when you're talking about Markovian open system general continuous dynamics. And finally, to actually get that all of this happens without us continuously measuring, we apply the judgment. So the judgment that my gambles at T1 do not depend, my judgments at T1, my judgment now that my gambles at T1 do not depend on whether I actually plan to perform the continuous measurement is then what gives us that we have a continuous evolution of the state according to that dynamics. All right, so brings me to my summary. I'll just tell us the things that we've learned. First of all, quantum theory is many normative additions to decision theory in a qubist reading. Secondly, measurement is the primitive concept, which is something that we wanted, but at least now have put on even more consistent grounds, I believe. Consistency with judgments surrounding measurement are what give structure, and that includes dynamics. And then finally, dynamics itself and also decoherence as a byproduct can be given a foundational formulation without invoking an environment, a non-selective measurement, or really any measurement or record. So we have our little guy who's wearing a QBism shirt, giving us a thumbs up. I don't know how many of those QBism shirts will actually sell, but okay, let me leave you with some outlook. So from an ontological perspective, we see that the essential ingredient is measurement. So we are even further inclined towards perspectives like what I talked about at the beginning, where reality is made by acting. And I think we're nicely helped along in this view because we didn't have an explicit or essential role for the environment in this story. Might make it easier to think about how that reality is made because we don't actually have something that's pre-existing just hanging around. From a reconstructive instruction point of view, the key has to be getting the shape of state space because dynamics are an epiphenomenon from our point of view. So things like the Qplex project and GPTs, et cetera, those seem to be along the right track, at least from my perspective. Maybe Rudiger disagrees, I'm not sure. And then finally, a technical research question or direction that I'm interested in looking in the future is translating and refining work on the so-called emergence of classical dynamics that decoherence facilitates, but translating all of that into lessons about measurement. So maybe at the end of all of that, we could get actual quantitative lessons about this so-called creative capacity of action. It's all fine and good to say that I take an action and I've created and something novelty comes into the world, but I'd like to measure that. I mean, I am a physicist, so that's it. The octopus will take your questions.
Okay, thanks so much for the talk. Questions?
Thanks for the nice talk. I'm wondering about a couple of things. Maybe you can chat more later as well.
Yeah.
But first question would be like where in this kind of epistemic onion comes time and space into play? It seems at some place you talk about T as this real parameter that you can just pick, and then you can reason about what if the time is 5 seconds or so. What state would I assign?
No, that is actually a really good question, and it didn't come in anywhere. It was presumed.
Okay.
So, like, I am assuming that my agents, at some point, I suppose, the agents have inherited some sort of intuitive notion of time passing, or at the very least, moment by moment. So, yeah, I think I'm appealing to like an instinctive time notion, but probably that can be unpacked more deeply, or we can get an onion that involves time too.
Okay, well, yeah, kind of. So maybe that's a follow up here. So because so I was expecting actually to hear before I actually heard your talk was more something like, what does it mean to at 5 seconds, for example, to have another state that would maybe a state assignment at a time. You actually have to look at your watch, like and condition on what you read there. So I wonder if you could phrase it alternatively or equivalently as saying, I have a clock variable, like I could have other variables, other systems, and I can certainly reason what say if two qubits, right? I can say like condition that reading qubit A gives me 0, what will qubit B tell me, right? So I think QBists can tell a nice story about that.
Probably, yeah.
I was expecting that you tell a similar story about clocks, perhaps.
That sounds, so first of all, it sounds like that might be a little bit more along the lines of like how beliefs do change in time. And remember, I was only talking about how we expect. So I don't know how we could say much about how beliefs do change in time, but also another point is, I guess it is implicit in all of this that the individual agent that is that we're considering has some notion of time for themselves, at least. Maybe it's not like universal for everybody, but we're only talking about one agent right now. So
yeah, okay, that makes a lot of sense. But maybe you can chat a bit more later.
Yeah, okay,
thanks.
I'm wondering how the emergence of classical dynamics would play out in this framework. Is it something along? Since we take measurements to be primitive, is it something along the lines of considering just a closed system, and then this closed system's constituents undergoes some kind of continuous measurements, and then we take the ensemble average, something along those lines?
I wouldn't say a closed system is necessarily involved. First of all, I did say that we're probably going to replace closed and open, but it's actually more in the open system setting that people would talk about emergence of classicality. So when I was talking here, depending on the kind of continuous measurement that I regard as irrelevant for my current gambles at a future time, well, that will have implicit in it the amount of decoherence that I expect to have happen, essentially.
So, what would the distinction be from the traditional decoherence modeling for classical emergence?
Well, if I'm doing exactly just this, then the math, once I get to here, is the same in the sense that I am just solving the Lindblad master equation. But we have justified the concept of dynamics, so one step earlier, before we get to the same math as before, we have a different foundation.
Okay.
That's essentially what's happening.
Okay, so let's thank again our speaker.